Hey, thanks for coming, everybody. I would like to talk to you about Apache Pinot. Apache Pinot is a real-time analytics database. It is, as the label says, fast. And I want to answer some questions about why. It's very interesting how you engineer an analytics database to answer in milliseconds rather than seconds. In my opinion, even more interesting to ask, why would you want a new database? And I think there's a bit of story to tell there. So you know who's telling it. My name is Tim. I live down in Mountain View, and I work for a company called Startree. We make cloud service, fully managed cloud service based on Apache Pinot. I run the developer relations team there. It's worthwhile to just, I think, have a brief history of, I don't know, computing. We only have 30 minutes here, so I'll make it brief. This is an IBM 1401. About 5 minutes from where I live in Mountain View at the Computer History Museum, they have 2 working 1401 machines. I saw one of them last Saturday. I won't say that I didn't weep. I won't say that I did, but I won't say that I didn't a little bit. It's really an amazing experience to see one of these things running. And it was kind of funny to note, you know, that the programs are stored on punch cards, input data is stored on punch cards, and the pain in the butt of getting punch cards read into the machine, I was thinking, yep, ingest is still actually that painful. Nothing has changed in 70 years. These were batch analytics machines. Okay, this is the dawn of commercial computing, 1959. Very few companies, governments were rich enough to warrant buying a computer, but those who did analytics on large batches of data. It wasn't until this product pictured here, you might guess, is the mid-60s, 1964. The IBM 2260 was their first standardized terminal product. And so now, by this time, computers are fast enough. There are interactive terminals. You type, you see characters, you provide input, you see output. And the idea of recording a transaction in a computer becomes a thing. So it takes a few years for the idea of a transactional database even to emerge. We start out in this batch analytics mode, and now all of a sudden we are recording changes that happen in the world live in a transactional database. Well, and if you wanted to know what was true, if you kind of wanted to do analytics on that transactional data, well, it was all in one place. Reporting was just a feature of the software. There was no analytics as a discipline. There was a report that you wrote somehow. Another funny detail, I was looking for a stock image of Green Bar. That's harder than you might think. They actually have boxes of it at the Computer History Museum. So if you're from out of town, Mountain View is about 45, 60 minutes away. It's a bit of a haul. Strongly recommend you go check this out. Anyway, a few years later, mainframes take over, you know, computing. Mini computers emerge, which are kind of architecturally the same. They're just cheaper. But then in the early 80s, we have this. We have the PC. So now computing is cheap enough where you have storage, you have I/O, and you have compute all in a cheap enough package that you can put it on the desktop of a manager, executive, knowledge worker, and that is a game changer. So you have, from the 50s until the 80s, essentially, I'm going to argue, an unbroken paradigm of you think you've written a monolith, you have no idea, the monolithic mainframe software. Now, all of a sudden, you've got programs running on PCs, and where does the data live? In some closet somewhere on a departmental database server. Now, all of a sudden, this is a thing. This caused a crisis in analytics. By the way, I was a nerdy teenager reading Byte magazine when this revolution was happening in the 80s, the client-server revolution, okay? And this was a revolution which was to have lasted for a generation. We are only just now seeing it come apart. And now that all of the data in the enterprise is squirreled away in all these databases everywhere, all of a sudden their decision makers can't get one view of the business anymore. And so what do? The crisis, or the revolution in application architecture from mainframe to client server creates a crisis in analytics, or reporting as it was called then, which gave rise to the data warehouse. Late 80s, early 90s, this is emerging as a discipline. Books are written, wars are fought, consultancies created, and this whole discipline arises. Now, the technologies that we were building data warehouses out of in the 90s and early 2000s are definitely considered legacy now, but that paradigm, just like the client-server paradigm, was pretty stable. Because what happened a few years after this? Some of you are old enough to remember Well, the web happened, all right? Seems like a giant revolution in the way we access computers and the way society works. I think that's fair. But honestly, the people who were building the early web were people who maybe 10 years ago were helping lead the client-server revolution. So how did you build a website? Well, you picked up your tools the way you built software, which was client-server, and you made websites out of that. And so that same paradigm incredibly survived the onset of the internet. The internet was built with client-server applications. And data warehouses kept ticking along. After a little while, say 2010, we start to realize, okay, we've got a lot more data from these websites, just a very different scale that we're recording user populations and building application databases that the old style data warehouse stuff doesn't work, so big data happened. And this, by the way, I think I asked Adobe Firefly to show me a picture of big data. And I like it so much. I never want to stop using it. It's like an electronic elephant. I think that really works. So this was definitely a new set of tools to understand, to do analytics and understand what analytics was all about. There were real changes that were ushered in, all new tool sets. But I'm going to suggest maybe not everything really changed as much as it might have, because you still had this idea that there's that application data over there, we're going to get it at some point, and we're going to put it here, and then we're going to do analytics on it over here. So it's a lot like a data warehouse, which is why we just changed the word from warehouse to lake, and that reflected some interesting changes in approaches to analytics. But it was still the basic idea that we're going to get all our data, we're going to put it there, and we're going to do stuff with it. Okay, so again, massive changes happening, and we're still kind of carrying this artifact, this paradigm of the way we used to do things with us. Around that same time, we started to use the word monolith as a bad word, this single application centered on a single database that was starting to be hard to test, hard to deploy, hard to scale, and crazy people started telling us, no, you should break that program up into 100 or 50 or 25 separate programs and have them all talk to each other around 2010, 2012. That was miserable, didn't work very well at all until what happened a few years ago. It seems like we figured out a good way to do microservices. Kafka entered the scene, and this notion of the event-driven application, a set of services talking to each other over Kafka topics, seemed to work pretty well. What happened here was the database at the center of our world kind of stopped being, the primary thing, and the primary place where data lived became a Kafka topic. This is happening right now. It is, I'm going to argue, the same kind of thing that happened when the PC became a thing in 1982. And that client-server application revolution, the way business software was written, utterly changed, and a whole new tool set, new stack, new set of programming capabilities, everything emerged. This is happening to us right now. As we go from monoliths, or the client-server paradigm that we all grew up with, into event-driven architecture. Just like before, when that application architecture revolution ushered in a new way of doing analytics, that's kind of what's setting the stage for things like Pinot now. I want to tell you just a little bit about how Pinot works. The talk is called Pinot, Why Are You So Fast? So we'll talk about why it's fast, how it's built, and I want at the end to just fill in some holes in this story and let you know where I think we're going and why Pinot matters now. All right, well, Pinot's a database. It uses tables. It's really not trying to impress you with any new and unusual data model. They're tables. It's a big box you put data into. But because it's a distributed database, it breaks data up into segments. Segments are how data is stored on disk. And even if you're not operating your own Pinot cluster, you kind of will have to think about segments and care about them a little bit. So it's worth diving into that a little bit. A segment you can think of as maybe like a 200, 300, 400 megabyte chunk of data. It's a bunch of rows in the table, however many rows there are. So you can have as many segments as you need, and we'll see how they get distributed later. Let's look at how they're built, though, because if you're going to be an analytics database and not a transactional database, you're going to organize your data on disk differently. If you're a transactional database, you're primarily interested in things. What's a whole row, right? I want to create a row or read a row, and you usually want a substantial portion of that row all at once. And so you serialize all the bytes of that row in one place in storage. When you're doing analytics, you are much more likely to want to scan a number of measurements, a single column. You want to get a bunch of those off disk in an efficient way, because probably you're scanning and aggregating a bunch of values. So imagine this data. I've got some little chunk of JSON, looks like clickstream data or something. When we create segments, we're going to take maybe 100,000, a few 100,000 of those rows, and all of the column values we batch up together. So all of the values of the IP column, the user ID column, remote user time, et cetera, all those get stored together. So columns are stored together on disk. So this is actually what it means to be a columnar database. So if you zoom in on one of those like bytes might be a good value that we might want to compute an aggregation over. If you look at that chunk of the segment, you would see a bunch of individual byte values lined up together. So at no point in a segment is a whole row stored all at once. We've grouped up, batched up columns together. And that's an optimization for being an OLAP database. Pinot is in complete control of its own file system, by the way. Sometimes people have asked me, what's it used for storage? Is it Parquet or something? And no. I mean, there are systems that you can use to query sort of arbitrary chunks and lakes, if you will, of data on in cloud storage, but that's not Pinot. Pinot has direct control of the file format, storage that's tightly coupled to compute. All that's in one place, and that's key to it being as fast as it is. So we've got all these segments, lots and lots of segments. Just give them numbers. They go on a machine called a server. As you know, naming things is hard. This is not a good name. It's not the only component in Pinot's physical architecture, but we call it server. So you have multiple servers. This is a component that you can scale arbitrarily, and servers are the place where the real work gets done. The actual storage of data and compute involved in query processing is almost entirely done on the servers. Clients don't talk directly to servers. Clients talk to brokers. What brokers do is they take a query in, they'll parse it, and they'll try to figure out which servers have the segments implicated in that query. So there are going to be predicates that you're going to have, and those predicates might provide hints about what segments are involved, and that might let you prune the number of servers that you have to scatter the query to. Hopefully it will. If it doesn't, then okay, you can just scatter it to everybody. But there's this interesting trade-off that it has to make between wanting to involve as few servers as possible, but also wanting to parallelize the work. So query routing is actually a fairly sophisticated and performance-sensitive thing, and it's another one of those things that takes place in the broker that's responsible for Pinot being as fast as it is. So the broker scatters the query. It says, hey, I need segments 2 and 8, and so I'll just find those servers that have those segments, send the query to those servers. The servers will actually perform the filtering and scanning and aggregation and send intermediate results back up to the broker. In this single-stage query example, which is sort of the default for how queries work in Pinot, what's probably coming back out of the server is either a scalar, right? If you're computing, say, an average of something, well, that's a number that comes back. Or if you're doing a group by, it's a set of key value pairs of relatively low cardinality. So you don't have massive amounts of data coming from the server back to the broker. The broker is then going to effectively reduce those into a single result set, send it back to the client. There is an option. Video's available online. I won't give you animations today, but there is a way in contemporary Pinot to have the brokers compute a multi-stage query involving various stages of servers for more complex things like joins and SQL window functions and things like that. Those are now supported in Pinot, and that plan looks a little more complex than what you're seeing here, but this is kind of the basics of a single-stage query. And for the basic filter and aggregate bread and butter analytics query, this works great. Overseeing all this is a machine called the controller. The controller's job is to orchestrate certain operations like loading new data, connecting to Kafka to ingest data, and making sure that metadata is distributed. So the brokers their primary responsibility is to keep track of cluster metadata, keep that picture in mind so they can do good query routing so that Pinot can remain fast. The controller is the one that oversees that metadata, storing it all persistently in Zookeeper as we do. There's this other little component off to the side called minions, and minions perform out-of-band maintenance tasks that aren't queries. You don't want them running on servers, but a very common and almost necessary thing that minions do is loading batch data. If you've got a giant collection of, say, CSV files in an S3 bucket, there's going to be a job that runs on a minion, creates those segments and loads them into the system. And that really is the physical architecture of Pinot right there, the basics of the components and how they work together to make a database that runs fast. And everything about this system is engineered to provide results in milliseconds, not seconds. And there are real-life use cases where you have actual queries of large sets of user data returning results in under 10 milliseconds, more commonly small numbers of tens of milliseconds. And to do that, you have to have control over your storage. You have to have compute and storage tightly coupled. You have to have compute and storage pre-allocated. You're not going to go find a place for a job to run when you've got query compute to do. You're going to... That's dramatic. We have an AV issue. You're going to send the query to exactly where the data is, and that compute is on standby, ready to go. Another way Pinot is fast is indexes. I'm not going to tell you about all of these, but these are the main ones. Some common things like there are a couple different kinds of text indexes, index for range queries, a specialized kind of range index for queries involving timestamps, all things that help you filter in a very efficient way when a query is being executed on a server. So indexes exist at the segment level, and so you have a query down on the server, that compute happening. Indexes help you read less off of disk. That's the idea. Since really, when you're scanning storage, you can only make that go so fast. Your next best option is to do less of it, and indexes help you do less of that. I do want to show you how one index works because it's kind of cool. It has a cool name, and it gives performance benchmark numbers. When people do like bake-offs with it, their first response is usually they think something is broken because it can't possibly be that fast, right? It has to be some sort of mistake. The result must be cached or something like that. And that is the star tree index, and it's hyphenated, and I have to say it differently so you know it's not Star Tree, the company that I work for. We just took, our name is an implementation detail that leaked into the interface because we thought it sounded cool. But the star tree index is not to be confused with the name of the company. Now, imagine you have, we'll say, some ad data. There's not a great deal of ad tech stuff that I see being done with Pinot, but there are a few kind of interesting, and people usually think of ad tech as somehow like a dirty business. We did about a year ago, a nice video with a guy who ran engineering for a company that used Pinot to do ad tech, and it was like really heartwarming ad tech, you know, like so you got your recipe blog and you want to be able to sell cooking gear on your recipe blogs. This kind of mom and pop ad tech, you know, very heartwarming. Let's just pretend this is that. And the query that we want to run is, again, the bread and butter filter and aggregate. I've got 3 predicates. Those are country, browser, and locale. I don't know which one of those 3 predicates is going to show up in the query. Some or all of them may. I've got one measurement, and that's ad impressions. And I want to aggregate ad impressions. We'll say sum. I want the total of ad impressions based on those predicates. What the star tree index does, and this is the only time pre-computation happens in Pinot. Pinot does not ask you to pre-compute anything. It doesn't do any pre-computation except when it builds this index. It builds this tree. And let's say you want, I don't know, all of the Spanish language impressions, right? That's just locale equals ES is the only predicate that shows up in the query. What are you going to do? Well, we'll traverse this. We'll go from the root node, and we'll pick the country. Country's the next level down. Well, wildcard for country, because we don't have country. And then browser is the next level down. We'll pick wildcard for browser. And then under there, we see, oh, well, 500 is the pre-computed aggregate for the Spanish locale. It's right there in the table. The index can contain, I can define other aggregates on other measurements, as long as this is my set of predicates. I can have as many aggregates stored in that node as I want, and you get essentially log n access to that thing. So it looks like a hack. This is where you can get, on petabyte data, you can get tens of milliseconds on real live aggregations, and you don't have to do any of that pre-computing. Let's skip a little bit to ingestion. I'd like to tell you how ingestion works, because that's part of the Kafka story, and then we'll finish up. All right, this comes from an example on dev.startree.ai, our developer site. This is a recipe that's in the documentation. Imagine you have this gigantic collection of CSV data you'd like to import. There's a procedure for how to do it, and if you wanted it to be more CSV data than that, that's okay with us. The basic idea is you're going to read this into a table, right? And like I said before, as you're reading batch data into a table, you're creating segments and loading them into that table. Well, what does that actually look like? Well, this data, you create two files, and they're both in JSON. So you don't ever type create table or anything like that. You create a schema file in JSON. You can reuse that between tables. That's one schema definition. That has your dimensions, your metrics, and your date time fields. Those are the three kinds of columns in there. And then, and you don't need to look at the details of this, obviously, you can find these online. You create what's called a table config file. That table config file gives the table a name, points to the schema, and creates whatever other configuration you want. If this were a create table statement, you'd have, it would say options, and there'd be that big bulky set of key value pairs. It would be sort of ugly. So here we are. And then you create the table, the command line command, and if you want to ingest the data, the only place you're going to see YAML and Pinot, you're going to create an ingestion job spec that looks like that, run another command, all of that to say, that's a minion job. Remember I mentioned those little minions down there? Well, that kicks off a job that gets distributed to one of the minion workers. It has access to the input file, and says, okay, we'll select you for that work. It reads into CSV and actually locally creates that segment. Remember that segment is like a 500 megabyte-ish file of input data? Obviously, you're not going to get 500 megabytes from that CSV file, but your data is larger. And the minion sends it to the controller, and the controller distributes it to a server, and then it's loaded and available for querying. So that's kind of how batch data works. Now, streaming data is really what this is all about, because Pinot came to life, it was actually created at LinkedIn 3 years after Kafka was created. So all of a sudden they had all these streaming data pipelines. They had to come up with ways of doing analytics on those for users. So they wanted live OLAP queries against live data just ingested from Kafka that could be in response to a page load or a tap on a mobile app. So something that's fast enough that I don't feel like the app is broken or the site is broken. You don't have 15 seconds for a fast Spark job to run. It has to be right now. And so Pinot was created for that. Now what happens here is something very similar, except as I'm consuming from a Kafka topic, there's an in-memory data structure called the consuming segment. And that is queryable, by the way. So as soon as we ingest a message from Kafka, the query routing, broker, server, configuration, all that, we'll be able to query that consuming segment. So records show up in queries immediately as soon as they're consumed. But of course, it's in memory, so once it fills up, we flush it to a real segment on disk through that same segment distribution process, and then that on-disk segment data is available for query, just like any other data. So that's how Kafka ingest works. As soon as a message is ingested, it's available for query. And there are some there's some more details to this. Number one, this is kind of interesting. In the table config file, you actually specify bootstrap servers, topic name, credentials, anything you need to connect to Kafka. The table is configured to connect directly to Kafka. Once you create that table, it begins consuming from that topic, from the start, from the end, however you set it up. So a so-called real-time table in Pinot is a thing that is connected to a Kafka topic and ingests immediately. And what actually happens here is the controller will say, okay, here's this new table I see in the metadata. You, Mr. Server 1, you're going to connect to this Kafka topic, and you're going to consume directly from it. So if you know Kafka, there's no Kafka connect here. There's no middle stage of any kind. The servers themselves act as Kafka consumers. And so it'll consume, fill up the consuming segment, flush segments, and so on. In fact, it even gets a little better than this, to where servers can do this in a partition-aware way. So if you've got a query that uses as a predicate your partition key, sometimes this happens, right? However those Kafka topics are partitioned, if that shows up in a predicate, well, I can make sure that every message with that key that is out there in that partition is always going to be on the same server. Asterisk, almost. We're going to do our best to make sure those segments land on that server. And the brokers are going to be aware of this, so we get to do pruning and we get to make Pinot very fast. We get to use that as a little optimization when it's available. Because again, the servers themselves are Kafka consumers directly. So there's all kinds of things built in here to make this fast, to make it I've always described the Kafka integration as a very intimate one. Pinot grew up alongside Kafka. When Kafka was, barely learning how to replicate data, Pinot was being created, and has very much grown up with it, and it's a smart match. I don't often describe Pinot this way because if you don't know what Pinot is, if you haven't kind of been through this little half-hour explanation, it's not helpful. But one can think of Pinot as queryable Kafka. That's not a complete account. There is more to it than that. But remember my history, right? I said we started with these batch analytics machines, loading data in punch cards. Suddenly the idea of transactions became a thing. Reporting was still easy until it wasn't, because there was a revolution in application architecture. Client-server began to displace mainframes for most new development. And so we had to invent a new way to do analytics. That's the data warehouse. The web didn't break any of this right away. It took 10 or 15 years, but then it started to break it. And we created big data because we wanted even bigger data warehouses. And we realized, wait, the way we've been writing applications has to change. And that got us into this event-driven world that we're all living in. And before this transition, we kind of knew how to write applications, right? There was a database, and you had a language. You were going to use Java or whatever it was. Maybe you had some rough circumstances, and it was Scala. Anything can happen, right? You pick a language, those languages back then, and you've got your database. You maybe pick a web framework or some limited number of choices to build that application. Everybody knew how to do it. The choices were put out. It seemed like it was hard, but it wasn't. They were all right in front of you. Now, you've got application code that you're writing. Sure, this is my stuff in microservices. And at the bottom down here of the stack, there's a bunch of Kafka topics. But in between, it really feels like wild, uncharted territory. And this crazy land grab for what is going to be happening in the stack there. It's a hard time to be a developer during this time of transition. This would have been like if you had been a mainframe developer in 1985 and you got a job doing client-server things. Everything is different. You don't know how to do anything. And this is where we are right now. We're trying to figure that space out. One of those places, one of those new parts of the stack is Pinot. We have to be able to look back at these streams of events that are now ruling our lives and ask what's happened and get insight into what has happened. That's fundamentally what an analytics database does. This is one of the parts of the stack that I think we're going to find is critical. If you want to know more, join me, Star Trek Community Slack. You can Slack me, you can ask other people, point you to other resources, got lots of videos, sample code, documentation, everything you need. Thanks for being here. Question. Are we doing questions? I love questions.
Yeah.
Okay. tell me when to stop. I'll stay here until the panel.
Thanks for the talk. You mentioned at some point that the storage is tightly coupled to the compute. Makes sense that that's how you would start? Is that what you guys are sticking with? And is it by design? Is the sort of an assertion that you can't get the kind of latency numbers you want by decoupling storage? Just curious what you think.
Good question. I like it. Almost planted, but not. And if you will pardon me, I will veer off into commercial territory because that's where the answer exists right now in Startree Cloud, the managed service. We have a tiered storage extension, and if you go YouTube and look for Startree tiered storage, you'll see a video where the engineer who led that effort, her name is Neha Pawar, she and I appear to be writing in thin air, talking about how it works. It's very cool. Obviously, it is slower, so parts of segments can now be stored in S3 in Startree Cloud, or Cloud Blob Store of your choice. Of course, it's slower. It's a lot less slower than you might think. There's some clever things in there. So yes, of course, we're going to negotiate that, and that'll leak into the open source product at some point. You know how these things go.
Awesome. This is great, especially for the notion of Pinot. For customers that particularly use Pinot production, what would you say are the statistics for how big the cluster scales and just the overall magnitude of the growth of Pinot as a whole, as a stack?
So how big are?
Does a particular customer use or scale Pinot to the furthest today that we know?
It's funny you say customers. I'm not on the customer-facing side of things in devreal. I don't mix with sales. I try not to. No, that's a joke. I love sales. Typical production deployments are, you might see tens of terabytes, hundreds of terabytes. You'll see some petabyte deployments, and some folks have presentations that we've got on the website, videos where they talk about those. But yeah, many, many terabytes, small numbers of petabytes.
Okay, I think that might be it for questions. Table 2 outside afterwards. So.
Table 2?
Yeah, Q&A table 2 if you have further questions.
Oh, I go to table 2.
Yes. Please do.
TIL. I would love to see you at table 2. Thanks for being here.